Hello friends, I'm going to analyze a very topic from IKV, which is inherent safe design in the soil water process facility, and this is one of the white papers which was presented in the seminar. So I have got this paper now, which is Hazard 28, and now I'm going uh, to tell you something about how this to understand this paper for the in the terms that is easy to understand. So So I'm going to present my these papers and going one by one to give an insight that what is uh, the know-how from this paper, what is the key takeaway from this paper actually. So as the topic says that it is inherently safe design in soil gas processing facilities, and the introduction talks about the practical application of inherently safe design or ISD in engineering can be a challenge. Engineering disciplines are often restrained in their work output by standards, codes, constant requirement, and client wishing to reduce capital expenditure. The process system engineer may be seen as one of who campaigns, coordinate, and secure ISD. However, in reality, in reality, the entire team is working in the same with the same constraint, which means that effectiveness of risk reduction factor. You can see that in the concept it is high, and feed it slightly goes down, and when you go to efficient and operation phase, uh, the effectiveness of risk reduction goes down actually. What it means that it means that uh, so basically inherited safe design or ISD is quite good if we design it into the concept phase. Then the effectiveness of risk reduction is very high when we do it in the concept phase. As long as we go in the advanced stage up to the detailed design, the effectiveness of risk reduction factor is less. So that is this graph is talking about. I'll just read some of the more lines which say that engineers require a sound theoretical knowledge and structural approach to assessing in engineering, and this should be integrated with an understanding of legal context, project client philosophy, risk analysis, and the broader project engineering objective, as well as constraints such as cost, standard, contract, and capex. Okay, so we will move on about the principle of inherently safe design. Pursuits tends to regard inherent safety as eliminating and removing the hazard at source, or using material or process conditions that are less hazardous. However, it is more helpful to think of ISD as a hierarchy or risk control, where risk control measures are applied in an order of priority, though application throughout the range is required to secure as low as reasonably practical. So it talks about LARP. The shell projects also talk about LARP when there is LDP, that the risk should be minimized as low as reasonably possible through the series or modification of the design. And this principle also in line with this one. The table also outlines the classic definition of ISD principle. So let's understand what this table is. It says that inherent safety principle is intensification, reduction of quantity of hazardous material. Intensification means that reduction in the quantity of hazardous material. Substitution like use of safer material. Attenuation means operation at comparatively safer operating conditions such as room temperature and pressure and liquid phase. Limitation of effects like changing the design and operation for less severe effects. Simplification, avoidance of complexity such as multiple product or multiple operation or congested pipe or unit setting. Uh, Error tolerance, making subject robust. Avoiding knockout effects like ample layout spacing. Making incorrect assembly like unique valve or piping system reduce human error. making status clear, avoidance of complicated equipment and information overloading, ease of control, less hands-on control. So you can see that these are the items which is basically helps to make a inherent a safe design. So if we're trying to implement these items during our concept phase, this will help us uh, to give a inherent safe design. Okay. Then application of inherently safe design in source service. So what do you mean by source service? Source service is basically the feed which is rich in S2S. It can go up to 3000 ppm. But if you open shell DEP, there is a toxicity and definition. It talks about different levels of S2S to make a service sour. So there are threshold limits up to which S2S is allowed and which cannot cause immediate death to the personnel. So any limit up to the threshold limit can be considered as toxic or sour service. There is also uh, a niche requirement that uh, if the partial pressure of S2S is less than say 1.5 psi, I need to confirm that number. It's not up to straight away on my head, but it depends on the partial pressure of S2S which determines that a system is sour or not. So you have to refer to the shell DEP about this one. I will discuss more about shell DEP toxicity and soreness definition in shell DEP, and then we can see into it actually. Yes. So that will be covered in the next chapter. So it says that hydrogen sulfide is produced deep in the oil and gas reservoir by bacteria that oxidizes organic compound to obtain energy. An estimated 40% of world's remaining oil and gas reservoirs are sour. S2S is highly toxic, flammable, explosive, and corrosive. Engineering companies develop design to separate oil and gas from the well fluid. The oil is stabilized, desulfurized, and desalted. The sour gas may be treated or compressed and re-injected back into production, a depleted and non-productive reservoir to give improved well pressure and perform through miscible flood and as a means of sour gas disposal. With the development of tried, tested, and proven process technology, compression and reinjection is taking place at increasingly high pressure and stress concentration. Given the relative cost of effectiveness and importance of engineering introduction of potential of major accident hazard as to with S2S over life cycle of the facility, effective application of principle of ISDs in the sour gas process facility is paramount. Successful application of the principle of ISD can improve HSC performance during construction, commissioning, operation, and decommissioning phases. So it talks about how S2S reinjection is taking place, how the world wells from which oil and gas is produced are sour, and there can be data also that how much they are actually, like what percentage of gas fields are sour. So basically this is a flow chart which talks about you know like inherent safe designs principle, and we saw this table, and this talks about activity and steps also. So let's go one by one on this flow chart, try to understand activities like identify all hazard and causes of these material action and condition, assess hazard, their cause and effects, and how this interact with the design, and avoid or so this one interacts with avoid or limit hazard by design, intensify, substitute, or attenuate to reduce the severity, simplify the process plant to reduce the likelihood of of the like reduced likelihood. So you can see this is interacting with the integrated safe design. So what happens that steps like identify hazards, understand hazards, avoid hazard, reduce severity, reduce likelihood, segregate, apply passive safeguard, apply active safeguard, apply procedural safeguards, apply residual risk reduction measures, and so these are the steps actually. And then it says that use finding a hazard assessment to eliminate risk and target and implement. So as soon as we go through the steps, we have to see some parallel horizontal aspects of that aspect. So if we go back to the top of the steps, it says that if you identify hazards, so the activity involved is identify all hazard and cause this material action and condition. Understand hazard, which means that assess hazard, their causes, effect, and how these interact with the design. Avoid hazards. Avoid or eliminate hazard by design, which in turn makes a inherent safe principle, right? Then reduce severity, intensify or substitute or attenuate the to reduce the severity. So that falls under inherent safe principle. Similarly, reduce likelihood, simplify the process or plan to reduce the likelihood, which also falls under the inherent safety principle. Segregate, use a distance or the section of the plant as a barrier to segregate, protect people from emergency. So this one is a part of step called segregate, and this also leads to energy safe design. Plus, other aspect is add-on safety, which interacts with apply passive safeguard, apply active safeguards, use active system, but now this depend on timely hazard detection, use safeguard that do not need initiation and hence have high. So these falls under add-on safety, and subsequently you can see that applying procedural safeguard, operator and maintenance procedure should be last resort, especially for control and mitigation. And then it says that use finding of hazard assessment to estimate risk. So from inherited safe principle, we used some add-ons, and these add-ons also talks about or interact with apply procedural safeguard and apply risk reduction measures. So you can see this chart is working in a synergy with different steps and activity to obtain a inherent safety principles. This is clear. Now we will follow some of the safeguard strategies, and we will go into details of other things like how it is achieved. Like safeguard strategies can be the process of constituting source material and increasing the pressure and temperature is in direct opposition of the concept of inherent safety, and that is to say limiting the hazard by using material and process conditions that are more benign. However, this does not prohibit effective risk reduction and management through safeguard strategy. The strategy for reducing risk, whether directed towards reducing the likelihood or severity, can be classified into inherent, passive, active, or procedural. Safeguarding strategy or engineering solution for the safeguard focus on passive, active, and procedural aspect of eliminating or reducing identified risk in the system. Passive solution represents features that are present at all time and require little human intervention to ensure they work. Active solutions include, for example, safety instrumented function and safety critical elements. They require an active system to operate and intervene, or an active managed design of integrity checks and maintenance to ensure they remain effective. Procedural solutions are those that are applied by the action of operation and maintenance processes, and they may require some engineered features to facilitate procedural application. The passive active and procedural safeguards highlighted in this paper are not exhaustive and blah blah. So what happens basically, they see safeguard strategies are Like it can be active, it can be passive, or it can be procedural solution, which means that active are from the instrumentations, passive that uh, like you uh, you make a system, like you generate a, like you select a material which is totally pressure or temperature compliant. And procedural is something like operator intervention. Like see, it says passive solution represent features that are present at all times and require little human intervention. So passive are something which human interventions are not required. Active one from instrumentation, procedural from the operator intervention. So these safeguards, when we work in synergy, can give you an inherent safe design, which is called ISD. Hope this part is clear. Then we will go to separation and segregation of layout. So basically, NFPA 30 also says that your plot plan separation should be such that in case they become different fire zones. Okay, so if there's a fire in this region, other ones can be isolated and blow down in a staggered fashion, and it is required to keep your facility away in a like 10 to 15 meters away so that they fall into different fire zones. So it says, you can see asterisk proximity toxicity zoning philosophy, red, yellow, green. So red, it said waste plot which is slug catcher, inlet separator, and expenditure. Prevailing winds are there in this direction, so this becomes a red zone. Central plot plan when control room becomes the green zone, and the yellow one is like engine recovery, hydroteters, central plots. These are the yellow ones. Solvent regeneration, solvent recovery, SRU is there, utility flares are there. So we will read through these sentences with the, and then try to understand. It said that global asset protection system, GAPS, understand asset protection blah blah, used for insurer usually sets a minimum separation distance to be applied in the facility. Driver here is to minimize equivalent damage, escalation and of the incident, and therefore ensures liability. GAPS sets out a minimum separation distance, taking into account cool fire and heat radiation, as well as that owner must undertake calculation for exploration. So basically, this is the same thing I was talking to you guys, that there are system where mm, uh, they talk about a uh, minimum gaps, and if we talks about some 10 to 30 meters away distances, and this one says that uh, this is augmented by a course qualified QRA or consequence modeling for explosion and or excursion events such as potential jet fire implement on a large hydrocarbon inventory. As the design progresses, the intra-unit spacing table is used to place items within the unit plot plans. Towards the mid to the late stage of it, the QR is developed that allows further plot optimization on the basis of risk. So you can see that this talks about QRA keeping the distance away, and it talks about different aspects of QRA, different stage of engineering. The overall plot layout can lead to some interesting challenges and dichotomies. Minimum separation distance is required to certify the insurer. Additional separation is required as per risk assessment to prevent escalation of major accidental hazard. Increased separation distance directly equals to direct cost. The CAPEX motivation is always to shrink the plot. However, the objective of the process safety group is not only to ensure sufficient spacing to prevent escalation, but also to minimize the pipe run, because from the point of view of unit safety, we want to minimize the available inventory to leak between two suitable points in the event of loss of containment. So hope this is clear and very well explained here. So the bottom pages are talking about uh, different zones, what is the meaning of that zone. So let's have a look on this aspect as well. It is usual for client to develop a stress proximity zoning philosophy whereby risk levels are determined for the units as as being high, medium, or low, as they are assigned in the zone red, yellow, or green respectively. The zones are segregated so that high risk red zones are located as far away from the occupied area of building as possible. The red zone is minimized to the extent possible, and the yellow zones are carefully delineated and restricted within the unit block. The assessment of the zone as red-yellow dictates operation requirement and working procedure to maintain a safe system of work, and this requirement are addressed throughout engineering. So as it is clear that prevailing winds are there, proximity of S2S, and then accordingly you define the zone based on the hazardous condition and the presence of hazardous material, which is red, yellow, and green. So we just go through the red zone, what exactly it means, and because only we will explore more aspects. A red zone threshold is a set level where serious acute toxic effects on the human body may result in fatal injury within the short time frame. Red zone work areas are strictly controlled. Non-intrusive work such as security and user inspection may be conducted with mandatory requirement for personnel to carry as S2S detector. So basically, these are the area where the high fatality can happen in case of exposure. So, anyways, I am not going to all this breathing system and PP is required, but prima facie these are the zone where exposure can lead to the immediate death of the person. So that's why it is classified as a red zone. Okay, what is this chapter talks about simultaneous operation or SIMOPS, and it states that S2S is highly toxic, flammable, and explosive. So the operator concern for separation and segregation is the health, safety, and life of the personnel. SIMOPS are where you have large workforce numbers undertaking the work. For example, campaign maintenance or a compressor repair in the close proximity of live plant. Or an operator may desire three gas compressor and condition trains to ensure the requisite available and production output of the facility, where it is known upfront that there is a requirement to be able to work in one positively associated gas compressor and condition train whilst the others are live. They require a SIMOP philosophy and increase separation distance in the design to support the operational requirement for safe working environment. So basically this talks about hot maintenance which is going on where the life is where plant is live and some train has compressor train has tripped and it requires maintenance at the same time. SIMOPS basically sees that how much operators are there in the live plant and which can increase the hazards and the consequence of the hazard. The simopsum threshold is set to a level where serious acute toxic effects on the human will result in the final fatal injury within the prolonged time frame. The objective of separation distance is that workers should not be exposed to immediately fatal concentration of H2S, and the separation distance gives them time to hear the alarm, recognize the emergency action required. An emergency safety mini filter breath apparatus and escape hazard to the temporary refuge. So it says that within a semi-pestilence proximity zone, there is a requirement to eliminate and minimize large number of people undertaking maintenance work whilst adjacent plant is live. It talks about SIMOF proximity where you have to limit the personnel who are working there and a safe distance should be maintained. The safe systems of work and design requirements very much the same as the red zone working. Following the provision adequate separation distance, SIMOPS work activities are managed through facility specific S2S STC ICG measurement, and it says that which incorporates the required permit to work, other requirements and needs to manage residual risk to LAP and ongoing basis through the life and facility. In terms of sum ups requirement, the design is a relatively new concept with increasing stress concentration, high injection pressure. It is welcome as welcome development. So basically, this chapter talks about CMOPs, it talks about red zone limitations of a personnel, it talks about permit to work. It says that total HSC should be there, should be proper breathing system is there, the exposure to S2S should be limited, so that it follows that the overall hazard is the minimum, which is as low as reasonably possible, allowed, and development of CMOPs and basically uh, CMOPs requirements where there is a requirement to limit and create a proper separation for the red zones is the new development and need to be incorporated into design phase of the project. Now the escalation of events talks about quantitative risk analysis and fire and risk assessment. So these are the health, like safety workshop, which is mostly done in feed phase. Concept phase, mostly we do desktop hazard and not QRA or FERA, but in feed and detail design we use this. Let's understand what they exactly is. The quantitative risk analysis, like QRA and FERA, enables the design to determine and uh, the credible escalation events, that is sustained jet fire impingement on the large inventory of a volatile liquid hydrocarbons, which can escalate to a boiling liquid vapor cloud explosion belief, which shoot fireballs and missile projectile. The studies also enable the determination of extent of the hazard, generally used to increase plot separation distance as an safer approach for the in the first instance. It is important to remember the escalation event must be credible. If the casual risk of belief exists, bullet tanks are oriented so that the end caps are not directed towards occupied building or area. It is very difficult to predict with any confidence the trajectory of missiles through where there have been studies showing that end caps generally travel in the distance of orientation, so the plot layout accounts for the line of sight of the end caps. So basically, this talks about like QRA and explosion risk assessment. Fire and explosion risk assessment enables the designer to determine credible escalation events and proper separation from the buildings or the inhabited areas. And this talks about that these the outcome recommendation from the QRA and FERA should be implemented in the design to avoid escalation of events. Then similarly, this talks about like plot layout. I will give some idea how the plot layouts is done. Like plot layouts mostly since says the separation plus the prevailing wind direction, and accordingly, proper fire zoning is done. Proper sectionization of the plot plan is done. So let's have a look on this one. It's like stress is toxic and acutely hazardous to health. Therefore, uh, Therefore, the overall plot layout must take into consideration a number of key HSC issues relating to prevailing wind conditions, which I explained just now. It's important that any temporary or permanently occupied buildings, construction, clouds, or instrument are placed upwind uh, of any large uh, credible loss of the containment events. This is inherently safe. So basically, they are saying that all this occupied buildings should be upwind, like in other direction of the prevailing wind, so that there is in case of fire or some other conditions, there is no immediate harm to the personals. Hope this is clear now. When the flare is operating as per design, the combustion of production from the solar flare like CO2 NOx, which is hazardous to human health. Under null condition, the flare may fail to ignite, causing flame out. Thereby, the solar material is dispersed into atmosphere from the flare stack. Again, they are saying that flares position should be uh, down of the prevailing wind, so that in case there is a flame out and there is a loss, or there is a outbreak of toxic gases, then it can go and disperse in the direction away from the habitat. Now, point number 3 says that with regard to the emergency escape, the temporary refuge, emergency escape, many filter breathing apparatus generally has 15 minutes usage limit. While theoretically the industrial filter medium can withstand 15-minute exposure, it's not good practice to push the limit. These constraints, coupled with the sound HC philosophy, enable systematic development of plot layout. For example, you must be able to reach a temporary refuge within 15 minutes from any location of the plant. Sensible assumption about walking speed and blah. So basically, this talks about. I'm not going to detail of this explanation, but it says that what I understood is says that plot plan layout should be such that your exit or emergency exit should be in a location which is more approachable to the people who are working in the plant and who are in the control room or the places or buildings where the offices are there. Plus, location of these buildings should be upwind, flare should be downwind, and most probably wind, so that in case of flame out or any other reasons where the flare has extinguished, the dispersion takes place and the toxic gases are not in the periphery of the operating plant. It's away from the it's dispersed away from the plot plant periphery or premises. So material selection is also a kind of a passive energy safe design, which means that you should follow a material which is compliant with the SOAR material uh, and which has proper coating. Like suppose it is a SOAR facility, then we go for duplex type or CS with some kind of coating for the equipments. So we will detail. We see what it says. This passage says, and then we will read it through, and uh, then we will analyze this one. Okay. What it says that in shore gas injection facility, there is an area where careful material selection is required due to presence of high stress content and extremely operating pressure and temperature condition. Established an integrated material selection and testing program ensures safe operation, which is why I have said it just now, that the proper selection of material is required for the ultra shore or shore S2S concentration, which is done by piping material guys to develop a piping material. And so what happens is aqueous S2S can create SSC, which is also called sulfide stress corrosion, and hydrogen embitterment, which is not good for SS material. So we go for duplex or some kind of epoxy lining CS materials. So let's go to some bullet points. What it says that where the injection pipelines have ground, pipelines construction from carbon steel based material are susceptible to embitterment, as carbon steel is known to have low temperature coefficient for heat conduction, and alloy rich materials such as F22 low alloy steel should be considered ideal for above ground injection pipelines, which is able to retain good toughness when subject to varying temperature. So one of the aspect very nicely spent when selecting material with excellent resistance to reducing an oxygen fluid such as sour gas. It's important for equipment as injection compressors, suction drum, and gas injectors, which are in constant operation with the sour gas fluid. Alloy material, nickel alloy, chrome alloy can be selected. So they are going for alloy material, then cladding of internal walls of the drums to meet design condition and prevent localized corrosion of the drums. Also, materials such as alloy 625 can be used for certain components. So very much say that no, they're not going for SS, rather they're going for alloy material. Air coolers are employed on continuous mode. There is possibility of overcooling of the standard process sour gas, which can eventually lead to the liquid formation in the air coolers, especially in the cold climate. The cooling tubes may be subjected to condensation, which can gradually lead to corrosion. Hence, employing a alloy-based material such as alloy 825 as a construction material can help reduce the risk if possible corrosion in the cooling tubes. So you can see that it's very clear that a proper material selection diagrams, or we call it material selection diagram, MSD, should be developed along with consultation with the process engineers, and they can tell us that how much stress concentration is there. Accordingly, material can be developed. So this chapter talks about this section talk about process pipeline and piping design, passive, active, and procedural design, and we will dig into this one, compression system, which is passive, leak path minimization, passive, and it talks about see it talks about compressor seal, then unrestrained pipeline, loop spacing, all passive, isolation, hard pipe venting, flaring, overpressure protection. It is active ones, hydrate and corrosion active one, enhance smart ping or pipeline inspection procedural, moisture analysis and wet condition is procedural, breathing air system procedural, and practicalities of achieving innovative safer design. And we will come to this checklist and all these things actually slowly, and then we will read through the conclusion. So let's go back to a system where it explains some of the passive active procedural innovative safe design activities, and slowly we will try to understand this. So what it says, the compressor system. The sour water compressor plant is the core of sour gas injection. In some cases, compressor can operate at pressure at 600 bar gauge with S2S level exceeding 25 mole percent. The need to select the right manufacturer with a proven compressor design experience at high pressure and sour gas application important. So they're saying that you should select a right uh, compressor type, the seal system, proper metallurgy, where the condensation happens. So, so this is what we understood from this compressor system. When high pressure, then leak path minimization, which means that high pressure operation for the potential leak and catastrophic failure of process equipment and piping become more likely. Hence, it is safer approach is to design your system for total containment. There should not be loss of containment. Total containment should be there. This means all process piping equipment shall be fully pressure rated to the withstand highest pressure that can be expected at all operating condition. So very important thing that you should design your system for full you should design your system with full pressure rating. You can see that it says that design your system for the full pressure rating, highest pressure that can be expected for the or operating condition. So very nicely told that it should be expected for all operating condition. A very simple example of designing injection compressor discharge piping and joint capable of withstanding the maximum possible pressure if outlet is closed. So you can see that full rating of the piping and the compressor components, so that it can lead to more not lead to the loss of control in case of blocked outlet. Somebody talks about improved seal design. So it talks this chapter. This one talks about flow induced vibration or AIV up to the exam of the components PSVs, so that there is no stress on the line and there is no vibration or AIVs induced stress on the pipe components, or which can lead to uh, loss of containment or breaking of the flanges. So it talks about typical expansion loops for the temperature differences. So you have to provide in case of thermal expansion, the proper expansion loops should be provided so that there's no stress on the line, and and it it is one of the best design to for avoiding stress on the pipes. Okay, so it says that to reduce such risk, like high pressure, high temperature, they call it now, can subject to high pressure and high temperature conditions. Let's read through this one. The expansion or the mechanical behavior of the buried pipeline under pressure and temperature depends primarily on the interaction between pipes and surrounding soil, and even more so with the sour gas injection. I've, so tests have shown that designing the gas injection pipeline as conventional restrained pipeline, high design temperature may introduce expansion stress and possible rupture. To reduce such risk, high pressure, high temperature pipeline may be designed to design an unrestrained heavy wall pipeline with expansion to buried in engineered backfall or padding to achieve the required fatigue life. So it talks about pipeline design, isolation, like you should provide proper sectionation of valves, fireproofing should be there so that you can isolate a system which is prone to leak or which has caused fire. Hard pipe venting talks about uh, proper hard pipe hydrocarbon drains or flare of the source surface should be provided through the bleed, having a low pressure drain including low point pockets from the initial line, hard pipe to the closed drain header. It talks about hard piping, flare that should be proper flaring system should be there, and proper uh, like disposal of toxic gases should be there through burning or incinerating. Okay, so it talks about purging and inerting the system for the maintenance and all these things. Overprotection active, like HIPS, talking about HIPS system, talked about seal certified system, hydrate and corrosion. That system should be designed to tackle hydrates or corrosion, like using alloy system for avoiding corrosion. Smart and pipeline inspection. So now we have sees the active ones, which is hydrate or corrosion. So water condensation and hydrate formation are serious one, and that's why we have to design our system to above the dew points actually. So it's talked about. So these are active ones. However, protection, whereas all these things are the passive one. Procedural ones are something which is like like inspection and moisture analyzers, breathing area system procedural is there, like providing proper breathing system. So this table talks about practicalities of achieving inherent or inherently safer design. This is like procedure or company documents are detailed. So there should be procedure, advantage and disadvantage. Talks about obviously having a procedure as advantage for your for advanced safety, and disadvantage, like the procedure may not be clear, the requirement may not be flowed, depending on the quality of the content. Then should be checklist can be there. Uh, it takes a large amount of legwork out of the task and makes it easier for project to undertake. Consistent area for verification application across multiple projects depends on the checklist. This one is that it can become a tick box exercise. Workshop should be there. It has advantages, disadvantages, mostly advantages, like you have to create some like QRA, FEDA and stuff like that. Then engagement survey, ISD trainings, competence effective for securing that competence and train your personals. Traditional risk studies, you see ALAP, HAZOP, hazard, LOPA has come to picture, which is we all do. So let's go through the conclusion one by one before we stop our video and understand this chapter. Like the process of concentrating soil material and increasing the pressure and temperature is an op opposition to be pursuits interruption of ISD, whereas the risk is reduced through modification to the material and process conditions. So what it said that plot plan layout, separation and segregation are the key components, and integrated material selection is the key component. Process pipeline solution is specific to the source cost to prevent passive active procedural safeguard strategies were outlined. So these are the key principle of ISD, and they should be followed. And what we achieve that, like, passive is compressor system, leak path minimization, uninterrupted pipeline, hard work, venting and flaring the passive ones. The passive solution is that features that present all time and do not require activation or action. Active one, overpressure protection of like hydrate and corrosion mitigation. Active solution are safety instruments, functions and safety critical elements. So overpressure protection, HIPS, seal system, procedural like smart pig pipeline inspection, moisture analysis, and breath air system. These are the procedural ones. So these are the key ingredients for the for ISD and achieving LABs. And it is always encouraged to design a system which is unity safe. So hope you like my video, and I would suggest that please subscribe my channel and do uh, uh, do like my videos so that I can post more such videos into my channel and increase knowledge of fellow process engineers. Thanks a lot, and thanks a lot for watching this video.